and welcome to the lecture of the experimental design um, class here in the artificial intelligence subject of the Faculty of Engineering at the Autonomous University of the State of Mexico. Today, which is Monday, the 13th of April 2026, we are going to carry out our lecture about uh, hypothesis testing. So I am going to start sharing my screen. Okay, okay. Well, so let us start. So first of all, I will share this file with you later on. So let us save as here. Let us use experimental design lecture. Today is 13th of April 2026. Agree? Okay. So this is the experimental design. This is the lecturer. My name is David Joaquin Delgado Hernandez. The program is Bachelor in Science in Artificial Intelligence here at the Autonomous University of the State of Mexico. The duration will be 180 minutes. Language English, and let's put date, which is 13th of April 2026. Okay. Well, so what are the topics for today's class? First of all, we are going to look at the estimation theory, which corresponds to the second part of the program. So the topics for today are 2.4, which is the estimation theory. The objective here is to evaluate and apply a point and interval estimation methods, specifically confidence intervals for the mean and variance to provide a probabilistic range for the performance parameters of an artificial intelligence system. That is the first topic for today. And the second topic, 2.5, it is related with the hypothesis testing. This is very important subject for artificial intelligence engineers. So the objective here is to formulate, execute, and interpret statistical hypotheses test to validate performance claims of artificial intelligence hardware systems and decide whether observed differences are significant or the result of random variables. Okay, that is the second topic for today's lecture. And we are going to apply this to the mousetrap card design in order for you to better understand the concepts that we are going to study today. Okay, so in first term, let us write this. How do we get from data to decisions? We have with one experiment, what we have to do is to collect some data. We modify certain variables and then we analyze what happens with our experiment. If it improves, if for instance, the distance of the mouse car trap is better than other experiment that we carried out with a different, for instance, lever arm, the size of the wheels, of the weight of the chassis, right? So we collect all this data and then we put all the information together and then we start analyzing. In this case, the statistics are a very useful tool for us to carry out the statistical analysis. And we have, on the one hand, the descriptive statistics. You can calculate the mean, the standard deviation, the skewness. You can calculate the kurtosis, but then you have now the inferential statistics where you can try some tests in order to verify certain hypotheses. Okay, so in this sense, what we can say is that descriptive statistics summarize the data, and you have here, as I said, the mean, the variance, standard deviation, and so on, okay? But then you have inferential statistics, which make decisions about a population using a sample. So in this case, for instance, you carried out some experiments with the mousetrap car, but you only tried, let's say, four different designs. Perhaps you tried eight different designs, right? Modifying some of the variables. But the idea with the experimental design theory is that you are able to predict the behavior of new cars, even though you have not designed or built these designs. Okay? So the idea is that you have a mathematical model that allows you to predict what will be the behavior of a car if this car had some of the variables that you already considered in the experiment. Okay, that is the idea. So let us put this in context with the example of the mouse trap car. So in this case, we test, let's say, 10 cars, 10 different cars with different lever arm lengths. And here the question is, can we conclude which design here, which design is best for all cars? That will be the question, okay? And as we saw last lecture, last week, we can build a graph, some figure, where you can see how the performance of the car improves while you are moving, for instance, the level arm, okay? But then you have a maximum point where you start decreasing again. So that is the idea of the test. When we test several cars, the idea is to identify this optimal point in order for us to design the best possible car. So in second place, we tried the exploratory data analysis that was made last week as well. So this is the acronym is EDA. And here, when we calculated the mean and compared versus the median, we could conclude something about the skewness, okay? Then we identify the outliers, and these ones affect the model training. So remember, when you have an outlier, it is data that is out of the range, of the expected range, right? We were saying that a car goes as far as 8.2 meters, another car goes 8.6, another 8.3, and so on. But suddenly, one car out of the blue goes as far as 25 meters. This is an outlier, right? Because it's out of the expected range that I am experimenting. Okay. Another concept that we saw last week was the normality. And in this case, we can say that this is required for many models. The point about normality is that many of the things that we can see in nature have this behavior. They are like a bell that allow us to see the mean value and the standard deviation, and then with these two data we can know many other things, such as the kurtosis. We can extrapolate this to the skewness and so on. So, for instance, if we have a wheel CD size and it varies, then the distance results may be skewed. Okay. Another point is that this means that a long tail. Do you remember Claudia Sheinbaum picture that I put in the previous lecture? So this tail, if this tail is very long, this means that some cars perform extremely better. So than the rest of the cars. So these are outliers, as I said. When something is too good to be true, you should be very suspicious, because that is not normally, at least in statistics, okay? If you see a very good performance of one car, be very careful, because you can be in front of an outlier, okay? Well, so then we saw in point number 3, we saw some statistical parameters. This is a review of the previous class in order for you to remember the concepts, and then we are going to put together everything. So these statistical parameters are, as you may remember, are the mean. In the mousetrap car, this measures the average distance. Then you have the variance, which is related to the consistency of performance. Then we have the skewness, which is related to the asymmetry of the graph, of the distribution graph. Then we have the kurtosis, which is related to the extreme behavior. Okay? So with these statistical parameters, we can analyze the shape of the distribution, okay, of our results. Well, for example, imagine that you have the same mean for the distance, but you have low variance. That will mean that you have a reliable design. So this means that you put the car on the floor, and it starts running, and it gets many times the same distance. let's say 8 meters, 8.1, 7.9, and so on. So it is always the same. The variance is very low, right? And the mean value would be 8 meters, okay? But what if we have some high variance? Well, that will be an unstable car. Okay, so imagine the first car, the design number one, has 8 meters as a mean value, okay? As I said, 8.1, 7.9, then 8.2 perhaps, 7.7, and so on. But the second design, imagine, has, let's say, 12 meters first, and then it has 4 meters. So look, the variance is so high, okay? But if you add up 12 plus 4, you are going to get 16. And on average, if you divide it by 2, 16 divided by 2 is as well 8 meters. That will be the mean value. But look, the variance is so high, okay? It is not close 12 and 4. They are very far away, okay? Again, you could have, for instance, uh, 14 and then 2 meters. These two quantities add up 16 once again, but they are very far apart, okay? So that is a high variance. That is an unstable curve. You cannot actually predict the following value because the variance is so high, okay? Well, let us now move on to the point number 4, which was the sampling theory. And we analyzed two important concepts, the large law of large numbers, which is LLN, and the central limit theorem. Okay, which acronym is CLT. Okay, so in the first case, in the law of large number, what we could see was that if you have more trials, you can get a more reliable mean. Let's put imply more reliable mean. Okay, well, on the other hand, in the central limit theorem, the average becomes normal. If you increase the number of trials, eventually you are going to get a bell-shaped form of the distribution. So that is basically the concept of the sampling theory. So in this case, for example, if you are testing only 3 cars, that could be misleading. That could be confusing because it is a very few amount of cars, only 3, it is not enough. But what happened if you, instead of 3, if you test 30? So testing 30 cars, you can get a stable conclusion. Okay? So be very careful when you are carrying out some experiments to try at least 30 if possible, which is the key number. This is the magic number in statistics because it is where the central limit theorem tell us about this distribution starting to behave like a normal distribution or Gauss distribution. It is the same. Okay. Well, with these ideas in mind, let us now go to our today's subject, which is the estimation theory. So let us put it here. It will be number 5, like the mambo number 5, okay? Estimation theory. Okay. Well, first, I have to tell you about the point estimate. This is a single value of the mean distance. This is a little bit dangerous in artificial intelligence. I cannot stay with only a point estimate because a point estimate just provide me with one single value. Okay, for instance, if I have to tell how far the car is going to run, and I said 8 meters, that is very dangerous because if I actually run the car, it could get, I don't know, 7.7 and I will fail, right? So what we have to do is to provide a confidence interval. So that is better, a confidence interval, which is a range of plausible values. So I can say when I am asked about the distance that the car is going to run, I can say it is going to be something between 7.5 and 8.5. Okay, that is my interval, my confidence interval. Because if I say 8, it is very probable that I will fail in the guess. Okay, but if I say and I give some two values, the inferior limit and the superior limit, it is very probable that I will be correct in this estimation. Okay. So in the example of the car, we can say that we are 95% confident that the real average distance is between, let's say, 7.5 and 9.5 meters. So I am increasing the range, so it is more possible for me to be correct in the estimation. Okay? So in the estimation theory, the idea then is to provide this interval. So the decision maker can have some elements in order for him to decide correctly, right? Let's say, imagine that you are asked about developing a new software for calculating some construction costs in the civil engineering area. And if they ask you how much it will cost, and you give a specific value, a number, it will cost 1,000 pesos, for instance, right? So it will be better if you say it will cost something between 900 and 1,100 Mexican pesos, because this gives you a a backup, okay? This gives you a backup for you to play in this interval. Okay, now let us talk about the 6th point is about the hypothesis testing. Okay, so you will see in every experiment that you are going to carry out that we normally have two hypotheses. The first or the null hypothesis, that is the name of the, let me write it down, is called H0, and it is the null hypothesis, which establishes that there is no improvement. When you modify one variable of the design, the first hypothesis that you will have is that there is no improvement, that everything will remain exactly the same. It doesn't matter that you have modified something in the experiment, but the distance will be exactly the same. What about the other hypothesis, which is called H1? This is the alternative hypothesis. Okay? This establishes that the new design is better. So you should keep in mind the following in this particular subject, right? These hypotheses are very common, for instance, in medicine, when you are trying a new medicine. Do you remember COVID-19? Well, all these big companies such as Pfizer, Bayer, and these very big companies started to carry out some experiments in order to develop the vaccine or the medicine to control COVID-19. Okay, so in the experiments they have to try so many different cases. For instance, they could have a man in his 40s, so they can have a woman in her 40s as well, and then try the medicine in the man and in the woman, and they see the result, and they can conclude if the sex has something to do with the result of the medicine. For instance, let's suppose that the woman improved quickly and the man didn't. So that means that the sex is affecting this medicine, right? Another case, they can try the medicine in children. For instance, one boy of 10 years old and one girl as well 10 years old, and then try it. If some similar behavior was observed, that the girl improved quickly and the boy didn't, so you can conclude once more that the sex is an important variable. Okay, so and look, in this case they have to reject some of the hypotheses depending on the experiment. So, but there may be some errors here. So let us talk about the errors. So errors. The type 1, this is called type 1. What it implies? Well, it's a false improvement. Let's go back to our example of the mouse car trap. So imagine that when you are testing your car, you are doing it in a flat floor, right? It is horizontal totally, 0 degrees of inclination. Okay, so you put your car and you start running the car and it goes as far as 9 meters. Perfect. But then you are trying the very same car, but in another surface. But now the floor is not flat. The slope, it's let's say 2 degrees. So it has an slope, an inclination. And you put the car and start running again the car, and it goes farther. So that means that the car, instead of running 9 meters, now it will run, let's say, 12 meters. But it is not because of the car. It is not because of the design. It is because the slope of the floor is affecting the performance of the car. And if you conclude that the car has an improvement, that is an error, that is a mistake, because it is actually not improving, but the circumstances were different. Where you put in first place in the experiment in the laboratory, you tried your car, there were some circumstances, and now in the new experiment, you have a different circumstance, and that is affecting, and you are accepting a hypothesis while you should not accept that hypothesis because it is not happening in reality. Okay, so let us put here the type 2 error, which is related with you miss a real improvement. So imagine the following. Again, you put the car in the laboratory and it is an horizontal floor. Perfect. It goes as far as 8.5 meters. Perfect. But then you put the car in this inclination and apparently it is improving the distance, but it is not, it is just because of the inclination. But what happened if you put it in the opposite direction? So instead of going down, you put the car for going up. It will cost more work for the car to climb this inclination, right? Because it is going to have this obstacle of the inclination, the slope. Okay, so what happens if you record a distance of instead, let's say instead of 8.5 of 8, but with the slope against you, that could be a real improvement. The car could have been improved, but because of this inclination, but now it is the opposite as the field experiment, you cannot identify that improvement, and that is the type 2 error. When you miss a real improvement, the car actually is better than the first design, but because you are having this inclination against, so you cannot record that improvement. So that is the second type of error. Let's say that you are trying, imagine the following experiment. You are trying a medicine, but the person that is going to try the medicine has got a flu. So this is a variable that you are not considering, but if the person has a flu and he takes the medicine and you cannot see an improvement, is because he had the flu. Okay, not because of your medicine, but because it had already another disease that prevents to identify the improvement. Okay. Okay, and here is a very important statistic, which is called the p-value, which refers to the probability that you have in your result is random. Okay. If this p-value is, let's say, P should go from 0 to 1. That is the value of P. Is something between 0 and 1. But if you have a p-value of, let's say, 0.7, so it is highly possible that this result is random and it is not due to the experiment that you are carrying out. If this probability is a very small value, let's say 0.0001, that means that it is quite possible that you are in front of an improvement, that yes, you are having a better performance. In the case of the medicines, imagine that some man takes this medicine and it improves his health improves a lot. So if you estimate this p-value and it is a very small quantity, again 0.05, it means that yes, the man is improving because of the medicine. Okay, it is not a random thing, but it is the result of the medicine. I am going to put another example. Imagine that you are trying to study mathematics. Okay, but at the beginning, you have many doubts. You are not sure about how to manage the mathematics and the formulas and things like that. But then you decide to take a special course in a mathematical academy, and they provide you with tools in order for you to improve your performance in mathematics. And when you carry out an exam, you get a perfect degree. You have 10 points, okay? 10 points out of 10. So that means that the tools that were provided in the Mathematical Academy were very useful for you to develop your exam, right? That is very possible that this academy is a good thing because you could improve your performance in the mathematical lecture. Okay. In contrast, where somebody didn't take these courses in the academy, so it will fail in the exam because he is not having these powerful tools to carry out a better exam. Okay, so we should be very careful with these errors, okay? So for instance, in our example, so you have a new lever arm versus the old design, the original design. So you decide to change the lever arm, okay? And you record a p-value which is less than 0.05. So this means that it is a very small value, and this is the critical value, 5%. So if you have this 5%, that means that yes, you have a real improvement. Because the probability of having a random result is very small, okay? For instance, if you have a p-value, which is, let's say, equals to 0.65, you don't have an improvement. Okay, because the probability of having a random result is very high, 65%. What is high and what is small? 5%. If you have more than 5%, that could be considered as some high value, okay? If you have less than 0.05, that is a small value, okay? So let us put an example here. So I am going to insert a table with some different experiments. So let me put a table. Okay. So the heads are going to be the design. Then I am going to move the lever arm, the wheel size, then the weight, and finally I am going to record the distance. Okay, so let me add a new row. Okay, so here let us put this design. This is just aesthetics. Okay, so imagine that I have the first design is called A, and the lever arm is short. The wheel size is small, and the weight is light. And you record a distance of, let's say, 8.1 meters. Okay. Again, the same design, A, short, small again, and light, but now I record a distance of 8.5 meters, okay? And the same thing, but now I record a distance of 7.9 meters. Okay, so I am going just to copy this. It's exactly the same design, but you are recording different distances. Oh, it is just like that. This. Control copy. Control. Okay, ahí está. Perfect. Well, now I am going to try a second design, which is called B, but then I will have a long lever arm, large wheel size, and let's say in terms of weight, medium. What happens with the distance? Well, now you record 9.5. Okay. What happened? Design B, the same variables, and the second experiment, you record a distance of 9.8. And finally, same values, but now you record a distance of 10.2 meters, okay? In all the cases, these are meters, okay? Perfect. Perfect. So let us build the confidence interval. So confidence interval. This will show, let us put here, shows whether there is overlap or not. So here, as you can see, there is no overlap. What does overlap mean? For instance, if I had here I don't know, 9.7, that will be an overlap because this 9.7 instead of 7.9 will be within these two values, okay? But here I cannot see any overlap, okay? This is 7.9, 8.1, and 8.5. This range is, let's say, on the left-hand side, and the following range is 9.5, 9.8, and 10.2. This is at the left-hand side, but there is no intersection between these two intervals, okay? So there is no overlap, okay? So in terms of the hypothesis testing, H0 would be that it is put in the Greek letter. So it is something like this. Mu A equals mu B. That means that the mean value of A is equivalent to the mean value of B. Okay? And the other is H1, the alternative hypothesis. You can say that now there is a difference between the means, and you can put it like this. The mean value of the design B is greater than the mean value of the design A. And what happens if the probability value, if P value is less than 0.05, so then you have to reject the null hypothesis, okay? So we are going to carry out an exercise in Excel in some more minutes, and I will ask you to follow me because we are going to program the Excel with all these formulas, and you will see how these behave in practice, right? We are going to carry out this practical exercise in Excel, okay? But for now, you keep in mind that if this p-value is very small, that means, as we said up here, that there is an improvement, okay? So there is an improvement. There is actually an improvement. So you have to reject H0 or the null hypothesis. The null hypothesis, remember, is that there is no improvement, okay? So this is the rule, okay? So let us now carry out this exercise. Please, everybody, be ready with the Excel because I am going to write the formula to carry out this exercise. So prepare the Excel file, okay? I am going to move to Excel. Okay, okay. So please follow me, okay? Please follow me. First of all, let us name this file. So I am going to save this file, and the name will be mousetrap car hypothesis. This, and I will save this. Okay. Okay. So here I am going to put the in the first cell, A1, I am going to put the experiment. In the second, I am going to put the design A. And in the third column, I am going to put design B. So imagine that I have two different cars, and I start moving the lever arm, I start moving for instance, the wheel size or the weight of the chassis and so on, okay? So in order for me to carry out this exercise quickly, I am going to put some random numbers, right? So in the first experiment, and let me put here, so write this formula, please. This is equals imp dot norm parentheses. Because my Excel is in Spanish, I will write in Spanish. But if you have Excel in English, you should write it down in English, right? Because these are commands that Excel recognizes. Okay, these are formulas that are within the software Excel. So I am going to put here aleatorio, then open and close parentheses. And then I am going to put here the mean value, the mean value. So in this case, the mean value will be 8, and the standard deviation, it will be 0.4. And I click enter. So here you can see the formula here, okay? So I give you some seconds in order for you to copy this formula.
Teacher,
Yes,
I have a question. I have
yes.
the my Excel in English, but I don't know how to write aleatorio because
Random. It will be
random.
RND. It should be something like that. Let me put. So if you take any cell, you just write random, and let's see if it gets the command automatically. It should be something like random.
Okay, teacher, thank you.
Okay, perfect. Okay, so if I move this, because this is a formula, right? If I put anything in the Excel, look, the number here changes, okay? I put here something, and it is changing. It is a dynamic. It is always changing, but you can see that this is something which has got a mean value of 8, as we put here, and the standard deviation, it is 0.4, okay? So basically, what this means is that it will give you some values between, so it will be 8 minus 0.4, which is 7.6. I will put here 7.6, and 8 plus 0.4, which is 8.4. So it is going to give you different values between these two limits. Most of the time, it could be that there is some value which is lesser than 7.6, or another value which is greater than 8.4, but most of the time it will give you values between these two limits, right? Because we put these parameters here, okay? So, and let me put here, let me just take a photo of this. Uh, uh, uh. Everybody is here with me. Everybody has got this formula. Is it working? Okay. Let me put this here. Okay. So look here, here, escape. Look, I am putting here. This is a screenshot of the table that I already put in the Excel, sorry, in the Word document. Okay. So look, do you remember there were two designs? The first one was called A, and the second one was called B. Okay. So let us just put here, right? So what is the mean value? Let us put here. If I put 8.1, 8.5, and 7.9, that is the first design. So let us calculate the mean value. In Spanish, it will be media. In English, it will be the mean. Okay. Mm, 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 mm. Oh, sorry. It is not media. It is promedio, average. It is in Spanish. This is the correct command. Okay. Okay. This is the mean value. Okay, and the standard deviation. Let me see how is it is right. Mm, mm, mm. Standard. Ah, no, the desviación. Here, I think that this is the correct command. So I am going to put here these values. Okay. So these are the values, okay, for the first design. So I am going to update. So instead of 8, you should put 8.1. And instead of 0.4, you put 0.3. Why? Because these are the correct values from the example that we are carrying out in the Word document. Okay, so these are the correct. Okay, And let me now see the second design. So I am going to put here these quantities. So remember, this is the mean, this is the standard deviation. Okay, so if I change and I put here 9.5, which is the first one, then 9.8, the second, and then 10.2. These are the values, okay? So I am going to use this mean and this standard deviation in the column of design B. So I will write down the following commands. So it will be equal inf dot norm, which is the inverse distribution of the normal Gauss shaped bell. And then I will put aleatorio, open and close the parentheses, then comma, and I will put the mean value, in this case is 9.8. It is the one that I just calculated. And the standard deviation, it is 0.35. So please write down this formula. This is the formula for the second design, okay? Let me save this. Okay. If you already have this, I will delete this thing. So let me just write down in the Word. Okay. Okay, design, the mean is 8.1 and the standard deviation is equivalent to 0.3. And then design B, I am writing it down in my doc file. The mean was 9.8 and the standard deviation was 0.3, okay? 0.35. Okay, perfect. It is already recorded in the Word, so I don't have to worry about erasing these numbers, okay? So I am going to erase this. Goodbye. I am going to erase this. Goodbye. And I am going to erase this. Goodbye. Okay. So you should have this, okay? These three cells. Now, what we are going to do, please follow me. Be very careful. You have to have 100. So you please do this with me and go as far as 100, right? So it will be here. Oh, sorry. It should be 2, 3. Again, go as far as 100 here. Because we are going to imagine that we are going to have 100 different experiments, okay? And we are going to compare design A and design B, okay? So I already have 100. And what I do next? So I am going to move this cell, to copy this cell 100 times. Actually, it will be 99, right? Because I already have the first one. So I copy this cell. And look, I have random numbers which resemble the behavior of my car. For instance, 84, it is like an experiment that you have recorded 8.8 meters In this case, it will be 7.9, then 7.96, 7.95, and so on. Okay, so if you look at the numbers, they are very close together because they are resembling the first distribution. Okay, a normal distribution which has got a mean of 8.1 and a standard deviation of 0.3. And I have to do the same with the design B. So I copy this 99 times. Okay. And look, now I have 100 different data for the second design. For instance, number 4, you have 9.84. These numbers are going to be different in your Excel, okay? Because they are random numbers. So it will be a coincidence if the number was exactly the same. If it was identical, it is, well, something very unlikely. It is practically impossible, practically. But that is because we are playing with random numbers, okay? So everybody is here with me? Any questions so far? Okay, let us save this file. You are going to use this with some numbers that I am going to provide later on. That's why it is very important for you to have the correct formulas in the Excel file, okay? If you get stuck with something, please ask me. Ask me and I will stop and explain again, okay? Okay, so let us put here some statistics. Parameters. Okay, so be aware that every time that I move something in the Excel, all the numbers are changing in real time, okay? So we are going to put here the metric, and we are going to calculate here for design A and design B. So what will be the first metric? The mean. So here I will put the formula. In my case, because I am in Spanish, I will put promedio. And I am going to select this range from cell B2 until cell B101. Okay, so this is the range, and I put enter. That is the mean value, okay? I do exactly the same in the next cell, design B. I can just copy this cell, and it automatically update the information, right? Because it is now considering the values of column C, the third column, column C, and you can see this in the formula, okay? This is estimating the mean value in Spanish promedio, and the range of the cells is C2 until C101, okay? Perfect. Well, the second will be the variance. Let us estimate the variance, okay? The variance, the formula in Spanish for the variance in Excel is like this. You put var dot s and then open parentheses and put again the same values from B2 until B101. Okay, so I am going to close this parenthesis and then put enter. Here you are, okay? That is the variance. and you can see the formula up there. And again, you copy this cell and it automatically calculates the variance for the design B, considering all the 100 elements that are listed in the C column. Okay. Well, the following is the skewness. This is the third parameter, a statistical parameter that we are going to consider here. And in Spanish, the command for calculate this parameter is coeficiente asimetría. Like that, like you are seeing on the screen, you have to write down coeficiente asimetría, that is the skewness, and you provide the range from B2 until B101. Here we are, and we can put enter. So you have the skewness, okay? And do you remember when it was negative? That means that you have a tail, okay? And then we can put this in the next cell, and this is as well negative, okay? And you have the cells that have been updated. So this is the formula for the skewness, okay? Now, let us go with the kurtosis. We are going to calculate the kurtosis. In this case, the formula is very simple. You just write kurtosis. In English, you write kurtosis with K, and in Spanish, you write kurtosis with C. So you just write kurtosis with C, open parentheses, and then put the range of cells, which is again from B2 until B101. Okay, enter. So we have the kurtosis, and we copy this to the design B. Perfect. These values are smaller than 3. 3 is the critical value. When you have 3 or more, that means that you have a peak in the distribution. In this case, they tend to be flat, okay? They are going to be not very high distributions. We are going to see that, okay? So let us now put the confidence interval. We can put this very beautiful, right? Let me put it beautiful. So we can use this. We can put these borders, and we can put these borders. It looks better, right? It looks a little, we can put bold. This is just aesthetics, okay? We can put here bold letters. So it looks very nice. I like it like that. We can put here some shade. . let's see, for instance, this, and again here, some gray background. It looks much better, more professional. Okay. Well, let us now go to the confidence intervals. We have to estimate, it is called t-value, t-value. This t-value is, let me put it here. Okay. I am going to put the formula here. So let me just put okay. Here is the formula. In order for us to calculate the confidence interval, we have to have the mean value, which is this x with a head, and this t value, okay? Then the standard deviation and the square root of the number of samples or experiment. No, this is the formula, okay? So the t value in Excel, you should write in Spanish the following command. So it equals, you have to put inf dot t, the value t, and if you have two tails, you write 2c, and then open parentheses, and you write the critical value, which is 0.05. This is 5%, comma, and then you in order to see this n value, which is the number of samples, you put contar in Spanish. In English, I presume that it will be count, and you put the range, okay? So you select from B2 until B101. Here we are. You close parentheses, and you have to add up -1. Put -1 and close parentheses, and you put enter. Okay. This is the t-value, okay? So this is the formula. You have to write down this formula in your Excel file, please. Is everybody following me? I am going very slowly, right? Very slowly in order for you to have time to write the commands and have a very nice Excel file, okay? Okay. Well, then let us estimate the confidence interval, the inferior limit for design A. So again, this is going to be a large formula, so be very careful. So I am going to put here the following formula. Equals, you are going to calculate the mean value, which is this cell for A, okay? I am going to follow the formula, okay? I am going to put the mean value, which is F4, minus the T value, which is the one that we just calculated. This is the T. Again, I am just following this formula here, but now with values, with numbers. Okay, times. So I am going to put times, open parentheses, and I put the standard deviation in Spanish. The command is desp est.m. Open a new parenthesis, and I select the range of the design A. So I select all this range from B2 until B101. So I close this parenthesis, and this should be divided by, in Spanish, the square root will be raíz. In Spanish, will be raíz of the number of values or experiments. In this case, I use the command contar again and select the very same branch from B2 until B101. Okay, here we are. So I close three parentheses, 1, 2, 3, and I put enter. Here we go. That is the inferior value of the confidence interval for design A. Okay, so this is the formula. Okay, and as you can see here in the formula, you have plus minus. You have two different signs here. Okay, x plus t times s divided by the square root of n. Okay, perfect. That is the first limit of the confidence interval. When you use minus, you calculate the inferior limit. When you use plus, you calculate the superior. So in order to calculate the superior, you are going to write exactly the same formula. Oh, sorry. This is superior A. But instead of minus here, you are going to put plus. So I copy this formula just like that. And I paste here. Let me do something. I am going to put this. I am going to put the same formula, but instead of minus, I am going to put plus. And that's it. Enter. Perfect. I have already calculated the confidence interval for design A. Okay. It goes from 8.06 up to 8.18. that is with this data that we calculated here, this is our confidence interval for design A, okay? So it's exactly the same formula, just you have to change minus. Instead of putting minus, you have to put plus, okay? Now let's go with the design B. Okay, in design B, I am going to put inferior B. Instead of using the mean value of design A, I will use the mean value of design B. The t-value is exactly the same, but the range, instead of using column B, I am going to use column C. So what I can do is just put exactly the formula, but I am going to change this. Instead of F4, I am going to put G4, G4, which is the mean value of design B. And here, instead of putting B2, I am going to put C2 until C101. Sorry, C2 until C101. And here again, instead of using B2, I'm going to put C2 until C101. Enter. Here we go. This is with minus, okay? The inferior for B is with minus. This is the formula, okay? Okay, enter. And for the superior, I am going to put plus instead of minus. This is going to be B. I am going to put the formula to paste the formula again. And instead of putting minus, I am going to put plus. And I hit enter. And that's it. That is the formula, okay? So let me put this very beautiful. And this confidence interval are for the 95%. 95%. If I want 99%, I should put here 0.01, okay? If I want 90%, I put here 0.1. That is the secret for this percentage, okay? If you increase the the percentage of the confidence interval, the range is going to be very small. If you decrease the confidence interval, for instance, let's say 90%, so the limits are farther away, okay? They are open. Okay, this is for confidence interval. And now we are going to carry out the hypothesis testing. So let me put here hypothesis testing. How can we do that in Excel? I will show you. So far, any question? Everything okay? Okay. So here is the p-value. And I am going to write the formula. And this is the formula, okay? So you put equal. In Spanish, you have to write prueba t dot t. You open parentheses and you put the two columns that you are going to compare. So the first column is from B2 until B101. That is the first column. Then comma. Now you put the second column that you are going to compare. The second column. Okay. Then you have to identify how many tails do you have. In this case, we have a two-tail distribution. So you put number 2, comma, and you have to specify here what kind of samples do you have. You have two samples with the same variance, okay? So you have to put 2 again and close the parentheses. That is the formula, and you put enter. Sorry. So this is a very, very, very small probability that this is a random thing. It's a very small probability. That means that yes, design B is better than design A. Why? Because this is practically zero, okay? This is practically zero. This p-value, let me put it in bold and put here the background. This p-value, you see, it is 1.04 exponent to the minus 94. So that is zero in practical terms. That is zero. So that means that yes, design B goes further. And you can see, for instance, I am going to try any number between 1 and 100. Let's say 75. So let me go to experiment 75. 75. Look, 10.22 is much better than 8.2. That confirms our conclusion that design B is better than design A. I am going to try another number between 1 and 100. Let's say 37. Go to the experiment number 37 here. And again, design B performs better. Look, design B is 9.6, while design A is 8.0. Another number between 1 and 100, 99. Let's go to the 99 experiment. Here we are. Once again, the same result. Design B is better than design A. That is the conclusion that we can state with this result, okay? This is the point. So that means that if I move the lever arm with these results, yes, the design improved a lot, okay? Improved a lot. Okay. Okay, let us graph these two columns, okay? So what you are going to do, follow me, please. You are going to choose this column from B2 until including the head, of the column. You choose all of them, and here where it says insert, you are going to look for a insert graph, statistic graph, insertar gráfico de estadística. Okay? You put here, and you can look at the histogram. Okay? You put an histogram. Okay. And here you can modify the title. You put here design A. Oh, sorry. Okay, this is design A. Okay, and let us do exactly the same, but for design B. So you choose all these cells, then go to insert, and then you put statistical graphs, and you choose the histogram, and you put here design B. Okay, this is design B. Okay, and so let us put this in order. Sorry. Mm. Let me see how can I move this together? No, 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 no. Escape, Control Center. Okay, well, I want to put them at the top of the file, but I will have to do it manually. Let me go here. Let me go there. So I am just putting this at the very top of the sheet. Okay. Here we go. Perfect, 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 perfect. Okay. Okay. Do you already have this, everyone? Everybody has this thing? Okay, perfect. So look, there is no overlap between the range, okay? There is no overlap. So you have 8.0 until 8.17 on the one hand, but on the other hand, you have 9.72 and 9.88. So there is no overlap. And look, this is changing, right? Do you remember that the exponent of this p-value in the first example that I carried out was 94 minus 94? Now it is 9, it is 85, okay? So look, let us save this. And look the shape of the distributions, okay? This looks more like a normal distribution, right? Because you have some concentrated values in the middle of the graph. But here you have very small values at the left and very small values at the right, right? And most of the values are concentrated here in the middle of the graph, okay? So any questions so far? So let us do something because everything is has been already programmed. So if I modify something quickly, I can modify the rest of the things. So I am going to put here an extra row. So follow me, please. So I am going to insert uh, let me see 1 second, please. I am going to insert here. I am going to insert four different rows. So I put here insert. Okay, okay. Sorry, I will have to do it manually. Just one by one. Sorry, I wanted to save time, but it didn't allow me. So one by one, I am going to insert here, and I am going to insert here. Okay. Okay. So look, what I am going to do now is to put here insert. Once again, design A and design B. Okay. And I am going to put here the mean and the standard deviation. So at the beginning it was 8.1 and at the beginning it was 0.3 and design B was 9.8 at the beginning and then it was 0.35. These were the values, the original values. So let me put this beautiful and this, okay. So here we are. I am going to put this in bold and with gray background. I am going to put this in bold and with gray background. Okay. So what I am going to do now is I am going just to modify this command. Now in cell B6, I am going to put here, instead of 8.1, I am going to put here this very value, okay? B2, but you have to add this money symbol. So you put like that, pesos, right? Or dollars, if you want. And instead of putting 0.3, I am going to put the cell, this, which is B3, again with the money symbol, okay? Perfect. That is the modification that I carried out in the first cell, okay, which is B6 now, okay. And I am going to do exactly the same, but for design B. So instead of having 9.8, I am going to put the cell, which is C2, and I add the money symbol. Perfect. And instead of having 0.35, I am going to put this cell, but again with the money symbol. Enter. Okay. So I am going to copy this, and I am going to copy this. Okay, look, everything is dynamic. So everything is changing. It is like I think that U2 or some group called Play, I don't remember. Everything is changing. Something like that they said. Okay, I just remember this part of the lyrics of that song. Okay. Everything is changing and I don't feel the same. Something like that. Uh, 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 uh. Alexa, play Everything is Changing and I Don't Think the Same. Oh, Alexa didn't recognize that song. Anyway, okay, so look, what I am going to do now is to modify these values. Okay, I am going to save this and I am going to modify. So let's see. Let us suppose that I start running one car, and on average, this is a much better car. It's like the Checo Perez car. Okay, it's the Formula One car. It's very sport car, and it has turbo. This new car, and this car goes as far as not 5, nor not 10, not 15 meters, but 20. So it goes as far as 20 meters. Okay. So the mean value will be 20. Instead of 8.1, I'm going to put 20. And when I throw once and again and again and again, I realize that the standard deviation is very small. And let's suppose that the standard deviation for this car is just 0.8. Okay, look how this is changing, okay? And the second design, again, is like the Checo Perez car, and it is very good design. It performs very well. But let's see, the distance that I am running this second car, the design B, is 20.3. And the standard deviation is now 1.2. 1.2. Okay. So the question to answer is the following. Is design B better than design A in this particular case? What would you respond? Do you think that design B is better than design A? Look, it is better because the mean value is 20.3, okay? And the other is 20, so it is better apparently. But when you analyze all these values, and you see here the histograms and things like that, what can you conclude now? Look, the two histograms look very similar, okay? And you can have here, look, histogram A for design A. Do you remember Claudia Sheinbaum, right? The tail, okay? So this is negative. As you can see here, this value is negative. So you have this shape, look at the shape. And when you have positive, you have the shape for the other part. Oh, somebody is telling something? Okay. So you can see that, okay, you can see that the mean value is practically the same. But here the point is that you have overlap in the confidence intervals, okay? So look, for design A, you go from 1994 until 2019. And here you go from 1997 to 2039. There is overlap, right? And the probability that this is a random thing is very high. So the probability is much greater than 0.05. So in this case, the probability, the p-value, this is the key. The p-value is 0.36. That means that it is not better. This design is not better. It is very probable that they are similar. This point 36 tell you that it is very possible that the two designs are similar. There is no difference. It is exactly the same. Think in terms of medicine. In terms of medicine, when you have, for instance, the COVID-19 medicine, Pfizer proposed a medicine, right? So they have to try the same medicine in 100 different people. And they measure, for instance, the temperature uh, prior to the medicine and then a posteriori, okay? So they have two measures for the medicine. First, the sick person had some temperature, then he took the medicine, and later on, when they took again the temperature, the person was exactly the same temperature. So it didn't have any improvement. So it remained the same. But what happened when they arrived at the solution, the medicine, the solution for the COVID? What happened was that the sick person had some temperature, then he took the medicine, and later on, the temperature decreased very importantly, right? So it showed a improvement, a very nice improvement, right? When you have similar things, you don't have any improvement. And you can see here in this experiment that I carried out now that the design A and B with this data are exactly the same. No difference, no statistical difference. But what happened if this was, let's say, 16 and with a standard deviation of 4? Let us analyze. There is a difference. It is a better design. Design B is better. How do I know that? Because of this. This is very small. It is practically zero. It is less than 0.05. And there is no overlap. There is no overlap. There is no overlap in the confidence intervals. Okay? This is 15, 16, and the other is 20, 20.25 and 20.73. Okay? There is no overlap. Therefore, there is an improvement. So in artificial intelligence, you have to look for this p-value. If you are going to improve an algorithm, a program, a model, a mathematical model, or something, you have to try the original and then the new version. And if the new version provides this p-value very small, that is better. You have a better algorithm, you have a better design, a better anything that you are designing. For instance, let's suppose that you are asked to develop an algorithm in order for Netflix to recommend better the movies that a user can watch. Okay, so you try the current algorithm of Netflix, and you see that I don't know, this algorithm propose 10 movies to the user, and the user only watch 2 movies, okay? Because it is not so good recommending these movies. But you propose a new algorithm and you carry out all this experimentation, and you can see that your new algorithm now the user is watching not 2 but 5 movies. You propose 10 movies with your algorithm, and the user actually watch 5 of these 10 movies. So it is much better than the previous algorithm, right? So in artificial intelligence, that's why it is very important to carry out this kind of analysis. Okay, I hope that this explanation was clear. Okay, any questions? Okay, so what I am going to do now is I am going to put you in Teams, and you are going to carry out an exercise with this very Excel file. Okay, so any questions so far?
Teacher,
Yes?
so if we have a very small value in the p-value,
Mhm.
it means that our design is better.
Totally, yes, yes.
Okay,
The
thank you.
smaller the p-value, the better the improvement. Yes. If it is very high, this let us try. Look at this. For instance, you have the first design, which goes as far as 20 meters with 1 standard deviation, and the second design is 20 meters as well and with one. Look, because they are random, these shapes are different, right? But this is a high p-value. Okay, this is a high p-value, and it is not providing evidence that you have an improvement. Okay, not provide evidence because it is very high. But if I put here 10, let's suppose that you at the beginning had 10. Look, this is a very small, so it is double. Okay, it is much better. It is much better, this design, because it goes as far as 20, while this is only 10. It is very short and the other is very long. Okay, so that is the thing. Okay, well, okay, so let me another question. Okay, so let me put you in Teams. I am going to close this. So how many people are there? Okay, 18. So it will be 4 teams. I am going to create 4 teams. Mm, 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 mm. Here. Okay, okay. Please go to your teams and well, wait a second. I am going to write down something here. Let me just put here. Uh, uh, uh. Okay. Okay. So let me put the what you are going to do. Exercise in teams. Okay. There is going to be 4 teams. So in one, you are going to use two designs, A and B. So let me just I am going to put here this so design A will be this. Use this formula for design A, and for design B, you are going to use this formula. Okay. Okay, so team 2, design A. I am going to copy this in order for you to have all the same information. Okay, so just give me a minute, but so in the second team, what you are going to do is to use this formula. Design A and design B will be this. Actually, all the teams can do all the variations, okay? Okay. So team number 3, okay. Okay, it will be this. And team 3, design A. So it will be this. And design B. And you are going to tell me whether design B is better or not than the original design. Okay, that is the idea of this exercise. So let me just put this using these distributions. Okay, and finally, team number 4, design A and design B. So let me put the formulas here. Okay. We are going to use this. Okay. Uh, 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 wait a second here. Okay, let me put it here. Paste, special paste. And here in design B, we are going to use this. Okay. Okay, perfect. So let me put this like that. Okay. So let us do something. I am going to put here in bold, in bold, in bold. I'm going to take a photograph of this so everybody can see at the same time all the. Okay, perfect. So, okay. I am going to put this in the WhatsApp. Okay, so let us take some 15 minutes in order for every team to carry out this exercise, okay? So please join your team and carry out, all the teams carry out the same. Here the question is design B better than design A? That is the question. That is the hypothesis that we have. And you have to say yes or no in which cases, okay? Okay, I put that on the WhatsApp as well. So I am going to assign the teams. Any questions? Okay, so go to your team, please. I'll see you in 15 minutes. Mm,
¿Qué onda?
ah, let's see. Okay. uh, well, let us discuss quickly about the results. How was the exercise? Um, I am going to share with you my screen. I have developed a MATLAB script which is similar to the one that we did in the Excel file. So I am going to put here. I am going to share the screen. So let us see how the results were, okay? So I am going to try the one that said team one. So I am running this. Okay, so this is the distribution for team one. Let me copy this figure to the okay. I am going to put the team one. Okay, and I am going to copy the results. Okay, and we're going to discuss now these results. So the results are here. Mm, 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 mm. Okay, so I'm going just to copy this. So the first result says that yes, indeed, the design B is better. Let us now go to the case number 2. Okay, case number 2. I am going to put here in the Word file. Okay, and let me copy the results here. So I am going to share this file with you, okay? So I am going to copy these results. Here we are. Okay. Okay. In this case, it is not better. In the second case, it is not better. The design is not better than the original. Okay. Let's go to the number 3. Number 3. Play. Okay. Okay. Team number 3. Okay. Okay. Control paste. Okay. And these are the results. I am going to copy this. Here we are. Control C. Okay. Paste. And finally, team number 4. Okay. Team number 4. Play. Copy figure. And I will going to paste here. And then here the results. Okay. So here the results. Okay. Okay. Well, okay. So I am going back to the Word file. Perfect. So I have put here all the results. Okay. So if you use these distributions in the Excel file, you can have these shapes, okay, of the two designs, design A and design B. But here is the interpretation. Let me put this, get rid of the bold. Okay. Okay, so if you start calculating, you have to arrive to these values. The mean A is 8.12 and mean B is 9.49. And these are the variances, okay? The skewness and the kurtosis. So the question is which design has better performance and which is more consistent. So here I have estimated the confidence interval for design A and B. There is no overlap, as you can see, no overlap. And the hypothesis test is a very small value, which here in the MATLAB is zero practically, okay? So then, yes, the design B is much better than the original design, okay? Which design should be selected? In this case, the better design is for design B because has an average performance of 9.49 versus 8.12. There is consistency. Design B is more consistent because it has lower variance, 0.21 versus 0.31. The confidence intervals do not overlap, so there is a strong evidence of the difference. And the hypothesis test means that we have to reject H0, which means that we have to accept H1. So there is a significant difference, okay? Well, so the decision here is to select design B because it is statistically superior, okay? Well, in team number 2, here is the command that you can use in the Excel file, and you are going to get something like this, okay? These are the histograms for design A and B. And again, I am going to review the result. So I am going to put here this in, get rid of the bold. So look, in this case, in this second case, the mean values is 8.34 and the second is 9.14. But there is overlap here. Here there is an overlap, right? Because 8.40 is between these two values, between 7.46 and 9.22. So there is overlap. And look, the p-value is very high. It is greater than 0.05. So that means that these two designs are similar. There is no difference, okay? That is the interpretation. So the p-value is very high. So there is not significant difference, okay? Well, let's go to the team number 3. In this case, let me put this, get rid of the balls here. I am going to share this file with you, don't worry. Okay, here are the histograms for design A and B. And the mean value is 7.98 and the B is 8.36, okay? So there is no overlap in the confidence interval, as you can see. There is no overlap. And the p-value is again 0, so there is a difference. So it is better. The design B is better than design A, the original design, okay? And the final team number 4, look, the distribution now. The mean value are 9.18 and the mean value in B is 10.01. Look at the kurtosis. It is very high. It is greater than 3. And you can see that it is a very sharp figure, okay? In both cases, there is this peak. So it's very sharp, okay? This is the kurtosis, okay? And these two values, the skewness are positive. So that means that you have the tail to the right hand side. Okay. In both cases, they are similar, and this is because this is positive number. Okay. So let us see. There is no overlap. Again, there is no overlap, and the p-value is small. So again, it is better design. B is better design that the original design. Okay, this is hypothesis testing. It is what you should know about it. And well, uh, I don't know whether you have any questions, people. Okay, so let me stop the recording. I am going to stop the recording. Thank you so much, everybody, for your assistance.